Yeah, so the idea is now in this remaining hour just to have some sort of round table on the topics that we have discussed and also some brainstorming on what, as Alex already said, what challenges and what we are still missing in the field. There is still a lot of work to be done, specifically when it comes to applications. So we have developed really good models that still they need some tuning and some improvement, but it's also very important to talk about what is the necessity of the field in terms of the applications. So we have these models, now what do we do with them? So we have prepared just some kind of topics that we have collected during the sessions and the conference in general, the workshop. But the idea is that we can all engage, and we would like to hear your opinion on this. So we have just come up with some approach ranging from the need of different levels of theory and how not only how we have different levels of theory, but how to combine them. Also the need of including long-range interactions and an accurate treatment of those. Uncertainty estimation, which is something that is lacking in most of our models, and it's actually really important. Then also the need for better curated data, and also to know how we can actually, it's not just about creating more data, but doing it more efficiently and knowing what is actually missing there. We have a lot of data that has been computed at different levels of theory. Another thing is that, do we need more, and if so, in which parts of the chemical space? Also, improving the physics of the models, we need to impose certain constraints and certain terms into the models that make them more robust, as we have seen in some of the talks. Also exploring the chemical space, which is quite challenging, as you know, owing to the combinatorial explosion of chemical space, which makes it completely untrackable. And also on our side, related to most of this last remaining talk, the need of, we need HPC infrastructures for the creation of these models, but then can we make them lightweight enough that they can be running in simple hardware, like in simple GPUs? And this is something that is really active because we need to get it along with the development of new GPUs, new TPUs. The field is really active. And also one of the things that is not here that we talk quite frequently on this in our group is what do we do with precision? Because GPUs have different precisions, and the current trends in, for instance, LLMs or development of AI calls for lower and lower precision, which is fast and more memory efficient. But for us, for science, this is a challenge because even if you talk to certain people, they will say that double precision runs short for certain things. And now we are talking even about the mixed single precision or not even single precision. So this is something that we should also discuss. But the idea is that we would like to hear some of your opinions. So feel free to interact, specifically also on the needs of what applications do you think we are still lacking. There is still a lot of work to be done, but yeah.
Right, so I guess I'll start by asking, for certain systems, the potential energy surface between the gas phase and liquid phase can be very different, and therefore the stable configurations that are important. And so I know that in many cases it's cheap to do explicit solvation, but we don't always want to do explicit solvation. So have people thought about training or developing some sort of implicit solvation-based force fields?
Well, I don't know if I mean, of course, even we have seen some of the contributions here in the conference were trying to go in that direction.
I think we had a poster from.
Yeah, we had a poster. In fact,
who was that?
From that
person in the audience. Yeah. So can you maybe comment on this?
So we are working on implicit solvation and also training of machine learning. So making these foundational models, in my case specifically for organic lightweight and machine learning evaluation by exploring knowledge with also a degree of freedom. Currently it partially works, but we are still developing and improving in this direction.
But does this implicit solvation, does it require like some new data sets with and without water, or like what do you think? So what's missing, for example, for your work to be like really?
Yes, so currently we're doing a hybrid, so we are creating data sets based on the acoustic models and fitting the experimental data, but the experimental data, mostly observation free energies that we have, is very limited. We only have data for small molecules, so this would be something which is beneficial. I think a couple of weeks ago there was a data set which was published. I think it's or a model. I think it's called AnySolve, which is implicit a data set from implicit solvent DFT, which might help for pre-training the model to make it more generalizable, but yeah, we're still exploring the direction.
Thank you.
Yeah, and maybe to comment on that also, I mean, it's quite related to long-range models, essentially, the question, right? And to get the correct response properties of the interaction between whatever surrounding model. This, can be also in a QMML bound method, for example, the same problem, but yeah, for some implicit solvation model, essentially the same problem. And so these are related. So any advancement essentially in getting the correct response will also improve this. And I think this is really one of the most actively worked directions at the moment. And I think then the implicit solvation will fall out of this, actually.
I have a follow-up on the long-range interactions. So throughout this conference and specifically in the last hour, you talked quite a lot about the number of message passing layers and explicit long-range, non-explicit long-range. As far as I'm aware, also Victor Zamerling from Germany looked at this. I don't know if you're familiar with that paper, but to briefly summarize, for them it didn't seem to make that big of a difference. Is that, I don't know whether you want to comment on that or whether there's something we could also consider.
Yeah, I mean, I think that, it depends what people look at, right? So, for example, for structure of water, right, the density of water, you can use a model as a 5-angstrom catalog, get it right, but probably for the wrong reason, right? And this is what people don't tell you, right? So, if you have an ordered system, right, like crystal, and water actually, ice is very similar to that. So you basically have orientations of molecules or atoms that cancel electric fields, right? So you have a localized electric field, and then everything is kind of local, right? But only in the equilibrium state, right? And you actually saw it from my plots, I think, for the polyalanine, right? So when you have a folded state of polyalanine, interactions are more local than they are in an unfolded state, right? So close to equilibrium, interactions are way more local, right? So whenever you model something close to equilibrium, you don't care, but in the end, you actually want dynamical properties, and that requires evolution from an unfolded to folded, from a disordered to ordered, right? And in that case, long-range interaction actually very important. So it depends what you actually model, right? So many times for static properties, you will not see a big difference, right? Because you will get close, or you will start close from an equilibrium, you will just converge to equilibrium, and then long-range effect no matter, right? So much. Right?
Or for example, IR spectra is also quite easy to handle. So what, for example, I found a bit challenging in terms of the first manifestation of this long-range interaction, just describing the properties of a liquid bill layer. And I found out that if you do it in a very robust way with semi-isotropic NPT ensemble where you decouple x, y, and z coordinates, it's very hard to get the right structure of the liquid bill layer, and it's super sensitive to even if you include particle mesh effect or not. So these long-range interactions are both 14, 15 angstrom. And so I guess now that we have models that scale to large systems, we'll see much more manifestations of this limitations of the current description.
And do you think that you have, looking at larger systems, can you spot possible defects in terms of long-range interactions quickly, or do you have to wait?
So that's the problem. Yeah, in order to see actually the difference, you have to simulate big systems for a long time. If you simulate big systems for 1 2 nanoseconds, you will not see. If in small systems, you wouldn't see this as well. So this really is a scale problem. And it's been known in classical force fields, right? So again, in this liquid layer example or whatnot, you just get the wrong structure if you don't have the right description. For example, we had a colloquium talk by Jan Stuart Marink, and he's a developer of Martini models, and they're trying to develop models for the minimal cell, right, with coarse-grained force fields. And then he showed, they have this setup and stuff. So he said, now you will see the simulation of like first minimal cell, and then the simulation starts, and the outer sphere of the liquid just breaks completely. And then he said, so it turns out it's very hard to get the right tension and stuff like this. So I think that as we go to larger scales, we would need to handle this somehow.
Yeah, and another, I think, related interesting question is that when, of course, these effects arise when you look at large systems, long timescales, macroscopic effects, and eventually our true baseline is experiment. But in the end, and we don't know really because it could never be done, how good our DFT ground truth model that we train on is actually with respect to these experimental observables, because it was and will probably never be possible to fully run DFT to scale up sufficiently to these. And so, I think this is also like really the thing that we're now finding out as we're training on different levels of theory, that we get different macroscopic properties, but then you don't know, like, are you diverging from your baseline, or is there just is your model insufficient of actually getting the correct long range, right? And will you even be able to generate enough training data to even make it self-consistent with respect to the underlying reference ever?
I think it's also an important point that sometimes the machine learning force field that you train on the data is much better than the data itself that you train, because it's doing interpolation in high-dimensional space, right? And it's actually doing things right. It's a smooth interpolation. When you solve your DFT equations, right, you change your external potential, and you can actually fall on different surfaces, right? Your electronic levels can switch, right? And you can get actually quite nonsensical results. And your machine learning model will not follow that, because these are outliers usually, right? So it will actually make a better prediction than your DFT data. Right? And we've observed this for a very long time now, right? Since our original DTNM protocol, the first time we observed this, because we had huge outliers, right, when we compare the reference data. And we realized those outliers were extremely distorted molecules for which you wouldn't actually trust DFT. So I would say that the model is actually better than DFT, right? Than the training data. So this is also very, very interesting. So because of that, it actually makes sense to distill the trained models and to produce data, which has not been done. And the models are becoming so big, right? And the train of so much data that actually those models can be more valuable than the reference DFT function. Changes the paradigm, right? How we generate data.
Yeah, and also kind of related to that, if I may add, is the challenge of how to check that your simulations, because this is something that you struggle a lot, especially when you're in the community. It seems that people are really skeptic about the machine learning force field output, which, we need to do, because this is like a really advancing field. That's why we need uncertainty estimations, but at some point, it's what just Florian said, you cannot run the DFT reference data for a 200,000 atoms system. So it's either you go to experiment, or we start making the models more robust until the point that you can trust them on their own. It's a bit of a challenge. There are some other topics raised by people in the audience, on the online people, if you want also to address them. Well, the first one is maybe a bit too specific.
I think the answer to the first one is that they should just try different general purpose force fields, right? Not necessarily fine-tuning them, right?
Yeah. And also, someone is asking me on RMSE for radiation forces, what are the benchmark best reflects MD reliability? I think maybe Camilo might want to talk this related to?
Well, we're currently exploring some benchmarks that do not rely on just comparing how my machine learning force field evaluates certain structures and how DFT evaluates the same structures. So we are trying to do a more chemically sound, chemically inspired benchmark, seeing how well does our machine learning force field reproduce the potential energy surface in things like bond dissociation, torsions, vibrations, and we're doubling on also long-range interactions. And the idea is to compare not point by point how the curve is like expressed, but literally the curve as a whole, and to see if not only we have small error point-wise, but small error in the whole chemical whole chemical behavior. And what we expect is that this gives us more information on how the models can simulate chemistry generally, and not how they can evaluate energies or forces for some structures. Yeah, I think that's kind of the idea, right? But there have been a lot of proposed benchmarks like doing actually MDs and comparing some observables to benchmark like, quite directly how well they do on the MDs, but they're a little more.
And also, I think like the point is that static benchmarks are not, do not convey the same meaning that you actually have when it comes to modeling physics or chemistry. So you may have as a little like really good absolute errors or mean absolute errors, and then your model is not. Or it's either doing it for the wrong reasons, or it's not actually that reliable across the different property spaces that you are actually trying to model, which is kind of an issue. So that's why we are kind of interested also to know what applications you may be interested in. Because I guess that as the number of applications that we are trying to tackle increases, then we need to, every time that we fine tune or we change a model, we need to make sure that it's actually performing well in the description of all of those observables. That's kind of the idea. And also the thing is that I think like everybody was kind of surprised with how fast machine learning force fields are being developed, and the things that were like never possible, I don't know, 5 years ago, now they are like surpassed, I would say. So the idea is like if you had an application in mind that you would like to have in 5 years, what would that be like? Which kind of things would you like to tackle? I don't know if also the audience is mostly developers or is mostly people interested in on the application side, is mostly chemists, physics, or biologists, but it would be also nice to have an idea of what, if you could have like one dream in the sense of one application that you would like to tackle in from 5 years from now, what would that be? Besides just going to larger systems.
And what's missing currently in what we have now? Or what you want to do?
I don't know, I think I already discussed with some of you about this ionic concentration in the simulations. So, I don't know what is your your ideas like in that direction, especially for RNA simulation. In our case, we did a dimer, but the dimer is just one ion. So, but then you have very complex RNA structures where you have to consider like certain experimental ionic concentration, and that is more difficult to simulate, especially now with the long-range interactions and so on. Then, how you are planning to address this kind of problem? So, like, build a new data set, like with long-range interactions with specific ionic concentrations, or like developing models. I don't know. So, you have some ideas in this way, or what is the plans?
Well, when it comes to ions, I'm not the guy, but I would say that that's a challenge also because, for instance, if you have something that it's really electrostatic based, you need. There is a lack of databases for that because you need. The electrostatic decays so slowly that you actually need specific databases to actually benchmark that what you're doing is is right. And of course, their solvation plays a huge role, because otherwise, in vacuum, you will never get the Coulombic separation of the system, right? So that's kind of an issue, and that's also related to, for instance, interfaces that you may have, like for instance, boundary effects that also put a lot of charges there. So I mean, yeah, currently I don't have an answer, but I think like in that regard, probably the biggest gap is the having access to actually good quality data when it comes to these long range systems and electrostatic systems.
Yeah, because I mean also it's related to the presentation from Alex. I mean, like you have like these models that they start failing after maybe 10 or 15 angstroms, and then you have in long-range interaction when you have the ions, right? Because you have the phosphate groups, and the ion is like maybe 15 angstroms, 20 angstroms apart. So then if your model cannot deal with that, then you will have to train like a really big data sets where they have all this information. So, but I think that's not...
It depends what kind of interactions matter, right? If it's just electrostatic-like, then you should be able to do it with the current models, right?
Okay.
Unless you have long-range charge transfer and you have population, depopulation of those states where the charges are kind of changing very quickly, not very quickly, but like basically the different environments, right? I think there's some work from Jörg Bella, right, on this basically changes in the chemical state, right, with respect to the ligands, right?
Theorem 2 and 3 plus.
Exactly, and so the states they change during the simulation, and basically, you know, he shows that some models fail, and you need to add more data, you need to make the model more, you know, expressive in terms of capturing those oxidation states, right? I think that there's not like a systematic benchmark of oxidation states, right? For especially for metals and so on, right? I don't think it's yeah, you probably need more data. But I don't think like, yeah, I think you can create this data for your specific systems, but it also is probably just requires better data for exploring oxidation states systematically.
I think with the overall models now, there are quite a lot of different oxidation states in overall. Actually, we've been benchmarking them, and with the latest electrostatics models, you can actually describe these kind of things like Bella did out of the box with the OMOL models. So I think we are not so far. So the OMOL 1.2 version, the second version, has like tens of millions of metals with different oxidation states inside it. And I think there are still rooms to improve in terms of quantitative accuracy on the redox potential of the ion transport, but the basic properties, I think that I'm quite optimistic that we are not so far. One of the applications, because we are asking about that, like that interests me the most is interfaces, because as Alex said, like one way to probe the long range is to break the homogeneity. Because when things are homogeneous, things cancel out, and actually you don't see the long range as easily, and you need to go to very big system or long time scale. But as soon as you break the homogeneity and you put an interface, then actually you break the symmetry of the system, and the long range has a big impact. And as a model developer, looking at properties at interfaces is one of the best ways to see the failure of local models. And there are plenty of failures you can see. Like, it's super easy to find them. And always with long range, it's like sometimes you have like easy fixes that might not need like very complex long range to get there. But I think like to have a sort of generic model of interfaces in the next few years, that will be really the frontier in terms of model development. And it's also one way to validate our electrostatic and dispersion interaction while not having to go to like big proteins. Because if you simulate, for example, surfaces and their fields, or a metal and close to an insulator, then actually have a lot of physics that happens that are actually similar to what happens when you scale up biomolecules, but you just have it in a toy model that is very easy to control.
And as Gabor said, you don't want to just feed the data, right? You want to have the right model architecture that describes this with little data, right?
Yeah, exactly. Little data, and especially being able to extrapolate to new kind of interfaces. And because you have like so many mix and match kind of interfaces you can do, you can really probe like the design space of these long-range effects, polarization, all of that in toy models. So that's how I think about like the model development in the next few years, because trying to make like big biomolecule benchmark with DFT, that will be hard. I mean, we will need a bit of them, but I think it needs also some toy models to also improve slowly.
I think you also about the data set side, because Omar was mentioned. I also did a couple of tests where I just wanted to compute the water exchange rate of metal cations in water. I would say a very elementary quantity, and if you look at the OMO data, which contains a lot of this metal cations with water around it, you would expect it worse. Like it was quantitatively well. What it does really well is equilibrium structures, like RDF it predicts really well, but for example, if we care about the area, it's much harder, and it's much more depends on the specific cation issues, how highly charged it is. So in this case, I'm not even sure we are close to there for on the data side, because for static properties may very well work, but if you actually want dynamics, I would say almost that probably still some gaps. I mean, more than we.
I mean, it doesn't have enough equilibrium structure.
I think so. I mean, if you just it out of the box, if you just put your metal cation in water correctly, gets the coordination number right, it gets the distances right to like 0.1 angstrom. Or even less actually, 0.05 angstrom, I think it was. Like the RDF looks qualitatively fine, but as soon as you want to like have something being exchanged. I was looking at the water exchange rate because it's a textbook quantity. You can find a lot of reference data on that. Like essentially the activation barrier for water exchange very much depends on the identity of the cation. So, and also on the other hand, for example, also tested a very interesting case of aluminium, which also the barrier was not, I would say, like could be better in terms of quantitative. But if, for example, got right that aluminium polarized water molecules to the proton, which I certainly is not in the OMO data. So like if aluminium draws the water molecule to it, it deprotonates it, which makes aluminium solutions acidic. So that again, so there's some kind of transferability, but it's not apparent if that is the normal, it will work, and if it's not the normal, it will not work.
I mean, OMO has no liquid or any kind of,
exactly.
It's only gas based, so if you look at ions in like liquids, then it will be hard.
I was doing everything in liquid at 3.
Yeah, exactly. So that's one frontier. But these things are very hard because to do like periodic things and non-periodic things consistently is not so easy in DFT. But I think that's also one frontier of having like bridging the gap. It's possible also that that's one hypothesis that once you have enough physics, you can actually extrapolate to the liquid easier, and that's something we've probably been trying to do for many years.
I mean, the model never failed qualitatively. It's not like it fell apart, and just that if you want really like not semi-quantitative but like quantitative experiment, because you can't really test against DFT for this kind of systems, as Miguel said. One way or another, the data doesn't seem to be, or perhaps the model, but we have long range.
I think it's a combination of two, but the data for sure. If you fine tune, you can get these things right.
And also, I would say that another necessity that we have in that regard is we have so many databases that are growing every day, but we really need to know what's in there exactly. You know, like because just as we have the periodicities in the periodic table for elements, chemical motifs are really repetitive in the chemistry that we know at room temperature and at pressure. So it's not about computing more and more structures, but it's like maybe we need to do that more efficiently, because for sure alkanes have been relatively easy to predict, but mainly because they are present in everything, ranging from a biomolecule to just aspirin or something like that. But we really need to have this, and we have found, like just like Alex presented in the case of atomic environments, if you do like an exploration of chemical motifs in terms of functional groups, you do see some correlations, like I don't know, tertiary amines that are not that frequent, then it's more likely to fail your model or something like that. So I think that this could actually kind of give another view on how is chemical space, and maybe it's just a repetition of chemical motifs that you can build in a more effective way, I would say.
everything that has to do with uncertainty quantification. So you have to be able to estimate uncertainty, right? And at the moment you cannot. At the moment you just compare the experiment, you see it fails, but you don't know if it fails because of the data, because of the model, right, or because of the experiment is wrong, right? So this can also happen. Right?
Yeah.
I think it's also a thing that people shouldn't take really for granted, that experimental data is out there, is reliable, right? Often it's not, because it's based on models, right? It's on some experimental observable, it's not a direct experimental observable, right? And it's like, for example, diffusion in solid electrolytes, right? I mean, what people measure is not diffusion in the bulk, right? They all confuse diffusion in the bulk, but they measure it in the surface. So comparing one-to-one is actually not possible, and you need to understand what's going on in the bulk and on the surface. On the event, you can compare, right? So you have to be aware of it.
But still, even if you had uncertainty, it would be, I don't think it would resolve the question if it's the data or the model itself, if it's architecture or data.
It depends. If you train different models, you can decompose the uncertainty, right?
Yeah, so certainly disqualify the experiment from being the source of error, but yeah, the data versus models.
Yeah, it's true. I mean, different models, by the way, trained on the same data, they give very different results. Sometimes, right? Sometimes they agree, but sometimes they disagree. You know, be careful about that.
But, I mean, the models also have a lot in common. So, if it's an issue with message passing in general, for example, and you wouldn't see it because they all fail in the same way. So, it doesn't allow you. It allows you to. It doesn't really allow you to see these kind of architectural limitations with a certain application. I think this was one of the questions that was asked on Monday.
Yeah, actually, I think this is a good point, and I would also actually like to advertise that we also should maybe think again a bit broader on architectures, because we're really converging on these graph neural network architectures, and I think more diversity would actually help to also answer the question to what extent, for example, our reference DFT data does scale up to experimental large observables. Because I think a lot of times the argument is made, oh, okay, so all these models trained on the different models trained on the same data converge to the same result, but then still doesn't really answer the inherent model artifacts if their models are just very similar and really borrow a lot of parts from each other. Yeah.
So, I mean, if you don't have any other comments, for the sake of time, we may just proceed to the final closing.